Okay, hello. The topic of this talk is a bit beyond the topics of the conference because it is devoted to the collective excitations in fermionic quantum liquids, quantum gases, superfluid fermions. But I hope that it may be interesting also for experts in superconductivity and magnetism due to a lot of crossing areas between those two fields. This work is performed in the University of Antwerp in the 2KC group, the theory of quantum and complex systems, in collaboration with Jacques Tampere and Hadrian Kurkdjian. The ultra-cold atomic systems are very attractive both for experimentalists and theorists due to a possibility to control the interaction strengths due to the Feshbach resonance. And the interaction strengths, the measured units of the inverse scattering length, can be tuned from the weak coupling regime, which is the most close to superconductors. It is the regime of weakly interacting Cooper pairs. And when we increase the scattering length to inverse scattering length to 0, the so-called unitarity regime, the regime of strongly interacting Cooper pairs. And further, we go to the regime, the BEC regime, Bose-Einstein condensation of molecular pairs, which are paired in the real space. There are a lot of experimental works about collective excitations in superconductors. For example, phase modes, and amplitude modes. The phase modes are the so-called Anderson-Bogoliubov modes of phononic. And the pair breaking modes are the so-called Higgs modes, which are closely related to the pair breaking continuum H. But they exist only in the regimes with positive chemical potential, so in the Bose-Einstein condensation regime they cannot survive. So those two types of modes exist both in the one-band and multi-band fermionic superfluids. But we here now focus also for two-band superfluids. Where the so-called Leggett modes can exist, which were predicted by Leggett and were observed in superconductors and predicted theoretically also for fermionic atomic gases, but not yet observed experimentally in cold atoms. This is probably the subject of future experimental study. Our investigation, theoretical investigation, is based on the path integral formalism, where we calculate the partition function as a path integral in Grassmann fermionic variables with a model action with the model contact interaction. In two-band systems, it contains terms that describe the intra-band and interband scattering channels, pairing channels. And the future way is standard as it was performed earlier for one-band system, starting from the paper by Sademel, Randri, and Engelbrecht. And in the same way, we introduce the bosonic pair field perform the Hubbard-Stratonovich shift of variables and integrate exactly out the fermion fields and arrive at the effective bosonic action, which contains two one-band actions, which are quite similar to the older theory, and the term which describes coupling between two bands with the coupling parameter gamma. So the first approximation in this way is the saddle point approximation, which gives us the set of coupled mean field gap equations, which are structurally similar to the gap equation for the two-band superconductors, but for fermionic atoms we have a different way to for cutoff using the integration with the renormalization of the point contact interaction through the inverse scattering length. And on top on the saddle point values of the gap parameter, we can expand the pair fields in powers of small fluctuations, keeping terms to the quadratic order, and arrive to the Gaussian pair fluctuation action, which is the basis of the study of collective excitations, because the fluctuation coordinates are just the coordinates for collective oscillation excitations in fermionic gases. The extension with respect to the one band system is that we have now four-dimensional matrix instead of two-dimensional for one band system, with the terms which describe the interaction between bands, and the collective energies of complex energies of collective excitations, which describe both the eigenfrequencies and damping factors, formally can be determined by solving the equation for determinant of this dynamical matrix, the inverse propagator of the Gaussian pair fluctuations. However, we have a problem to solve this equation, because the determinant has a branch cut at the real axis, and when we look at this picture, we have no roots for this equation. So, in fact, we have at least two ways to determine the spectrum of collective excitation. First, we can determine them numerically using the spectral weight function, or the response function, and just find peaks, the positions and the widths give us the parameters of collective excitations. And this is, of course, very reliable way. And the second way still try to find those roots. But those roots really exist, but they are hidden on this branch cut as behind some wall. In order to see something behind this wall, we must analytically continue this determinant, this function, to another sheet of the Riemann surface. If we perform this analytic continuation, this first was proposed by Philippe Nozière in his 63 book for green functions, but we use the same idea, and we see that we can, this analytic continuation opens a window at the real axis in order to find complex roots which can give us both the energy and the damping for the collective excitations. In fact, there can be more than one windows open in such a way because there are several windows which are separated to each other by the angular point frequencies. And this is, for example, the pair breaking continuum edge. This is the angular point line which is relevant, is important for the sound velocities, and those two are related to the higher frequencies. And if we find roots, complex roots for this, for all these windows, we obtain formally a lot of roots. Not all of them are physically relevant because some of them repeat each other, are images of each other seen through the new branch cuts in the complex plane as a refraction surface. But we can construct in this way the effective response function using all those roots and the corresponding residues and restore the analytic form of the response function. For example, we see here several spectral wave functions for the modulus and phase responses at temperatures rather close to critical temperature and even more close. It is especially interesting moment. I just have chosen this slide in order to see that we now can restore the mode which has a quadratic dispersion when we go just to TC. It was at precisely TC obtained in this work, but we now can follow the evolution of this mode at temperatures below TC. It comes, in fact, from the sound, one of the two sound modes, and we go to TC, the linear dispersion changes gradually to the quadratic dispersion when we go precisely to TC. One experimental check, I would like also to show it. We have got a remarkable agreement of the sound velocity obtained by our method using different sets of background parameters to the experiment by Chris Valle and colleagues about sound velocities in ultra-cooled atomic gas. And we see really the very good agreement of our predictions with this experimental data. Next, we also applied this technique to the pair breaking collective excitations, or so-called Higgs mode. What is the most important here? That it appears that there is a so-called Higgs mechanism, which is traditionally based on some low energy expansion, fails here because, in fact, the low energy expansion cannot predict behavior of Higgs mode near the pair breaking continuum, because they are pinned to this pair breaking continuum, because this is an essential feature which vanishes when we use the small energy expansion. And we have obtained an non-trivial dispersion for this pair breaking mode, and we also have found some difference between the old and recognized results by Littlewood and Warma. It now should be corrected. Finally, within our unified approach for all modes, we can also describe the Leggett modes in two band superfluids, which recently were experimentally realized in the ytterbium atoms using the so-called orbital Feshbach resonance, when the one long-lived excited state gives a possibility to open two channels for pairing. And we see first look here for the BEC regime, which just is realized now experimentally, and we can see that in contrast to the or common opinion that the pair breaking, that the Leggett modes cannot survive above the pair breaking continuum H. In fact, they acquire only a relative small damping, but they do not vanish in the continuum. So they must be observed in the future experiments. We can also show the response functions for the same regime, and we see that as a function of temperature, the Leggett mode frequencies can penetrate the pair breaking continuum, both for phase and amplitude response. What we can see here more is that the phase and amplitude response functions in the BEC regime are almost of the same magnitude. So the collective modes in the BEC regime, the Leggett modes, as distinct from the BCS regime, are presented here almost equally by phase and amplitude, while in the BCS regime they are purely phase. And finally,
you have 3 minutes. 3 minutes.
Okay, it's enough. I can briefly also show the results for the weaker coupling in the other pairing regime, BEC unitarity. We see here that our calculations, which does not use the low momentum expansion, but just numerically solves the dispersion equation, gives different results from the known low momentum expansion, and we see that we see a drastic change of the behavior of the Leggett mode when it crosses the pair breaking continuum. It acquires here a strong damping and continues to the above the continuum in different ways that is predicted by the expansion. This is one more argument that the low energy expansion, the so-called Mexican head of potential, cannot work. We must use our more extended approach. I can also confirm this analytic calculation of roots by the spectral functions as they with the phase response, the amplitude response. We can see here all modes together, the coexistence of and interplay of different modes. The phononic mode, which goes to the pair breaking continuum, and the Leggett mode, which crosses this continuum, being preferably phase mode than amplitude. And the amplitude response shows us also the pair breaking mode Higgs. And also the temperature dependence at fixed rather small momentum shows us all those modes again. And we see that Leggett modes can penetrate the continuum and exist above the continuum. Sorry. Now I can conclude that we have considered all modes existing in two band superfluids in one the same unified approach, and we consider them together. We calculate the spectra beyond the low momentum or low energy expansion, and find the agreement with experiment for the sound velocity, and find some new modes which appear when temperature goes close to Tc. In what regards the future studies, it can be straightforwardly extended to the charged superfluids. We have already some results, but not yet published anywhere, so I would like to only by words say about them. For example, that the plasma mode strongly suppresses the phononic modes, Goulson modes, as predicted by Anderson, when it is much larger for superconductors. But if the plasma modes goes to the pair breaking continuum, the picture is much more complicated and interesting. They all show some anti-crossings, and this gives us very nice pictures. Thank you very much.
Thank you. Thank you. Questions, please. First questions.
I have a small comment and question. Since the history of study of the Leggett mode develops very slowly, I could say it was experimentally observed in only into 2002 and published the first paper by Professor Ponomarev by 2003 in solid, and 2004 publications in the solid state communications experimentally, but at very small temperature, at liquid helium temperature. And the next work, which could experimentally show the dependence of the Leggett's excitation with the temperature, not at the liquid helium, appears. It's a work of Maximov, Karakozov, Ponomarev, just only in 2012. So I ask to the public to pay special attention to this today presentation of Professor Klimin, since it's in my opinion, it's a very important theoretical work which for the first time fully covers this field of the temperature dependence of the Leggett excitation mode and its coexistence and interplay with the gap H of the quasi-classical continuum states. So it was my comment and a small question. Could you tell me, please, you citing works of Blumberg as well as Lara Benfanta and other people from infrared spectroscopy, but it's funny because they claim something opposite to results of to your conclusions. They claim that the Leggett mode could cross the gap H and goes between the gap the two gap H's, so it could have energy between the large 2 delta and the small 2 delta and doesn't vanish, but it's opposite to your result. Could you
I also show that they do not vanish.
Yes, in Bose-Einstein condensation regime.
In Bose-Einstein condensation, they also go
yes.
to the continuum.
Yes. Yes, but as I understand, in the classical limit of BCS condensation, it should not. It's still
the classical limit
under the edge.
We did not obtain any that this is forbidden. We never see that it's forbidden in our approach. But there, some people claim before that they cannot exist in continuum. Not me.
Okay. Okay, thank you.
Second question, Abdullah, please.
I have only one yes/no question. As I understood, in the BC regime, your equations have only one solution, and this gives Goldstone mode with the real sound velocity. This is true? Just imagine that we are working on the BC regime.
Sound velocity has damping in origins. Yeah. Sorry. Sound velocity, as we obtain it, has no non-zero damping in all regimes. Or it is a subject of our our previous paper in. I can. Sorry. Yes. Yes, if you, I can give you send you reference to this paper about sound modes, and they have non-zero damping, strictly speaking, in all regimes.